Edpuzzle. All right, so today's topic, we're going to talk about geologic time and fossils. And then our activity is going to focus on the fossils found in Virginia in particular. Let's take a peek at our learning targets. We're going to learn about geologic time, how we sort past events, and then we're also going to talk about fossils. You will understand how old Earth is and how we know uh, the Earth's age. So you've been successful today when you can identify when humans first existed and which organisms would become a fossil. So the first thing I want you guys to do is just give me a little bit of feedback about what you know as it stands or at this moment. What are fossils? Where do they come from? How do they form? What happens for those fossils to um, how did those fossils get to be, basically? And why is it important to study fossils? If you don't have an answer, you can just write you don't know and or just give me a little bit of whatever background knowledge you do know. Okay, so the first thing I want to talk about is paleontology, and that is the study of prehistoric life. So if we break down that word, just because you know I always like to break down words, when we're talking about ology, anything with this suffix means the study of. Okay, so anything with ology, biology, sociology, psychology, paleontology, that is the study of. So in this case, the root word paleon, that's going to be prehistoric life, the study of prehistoric life. Easy peasy. Okay, so paleontologists are scientists, and these are scientists who are analyzing fossils to describe the Earth's past, to talk about um, evidence that we have, evidence or proof of prehistoric life, and even climates too, prehistoric climates too. How old is Earth? So we know that the Earth is 4.6 billion years old. We talked about this in the beginning of the year, at the first unit during astronomy. How do we know that? Um, that's what we're going to talk about later with fossils. But the first thing we're going to talk about is the geologic time scale. On the right hand side, you can see the geologic time chart. This is how we break down certain periods of life on Earth, okay? Because we've been around a long time. I mean, 4.6 billion years is a long time. So in order to kind of make sense of everything in terms of life, um, we break it down into different pieces, okay? And each of those pieces, like the chapters basically, are marking big changes on Earth, whether climate changes or um, animal changes. So it could be mass extinction events. So the last major change was 66 million years ago when an asteroid hit Mexico, and that's that asteroid that killed all the dinosaurs. So at that time, it killed 75 species, 75% of the species that were on Earth. That's a chunk of the life that was around. And humans, us, we haven't been around but a very small amount of time. So the geologic time scale is basically how we break it up. And the way that we break it up is by the biotic composition. So remember we talked about abiotic and biotic factors in other classes. So biotic means living. Just think about bio is living. So we also talked about index fossils. So index fossils definitely helps us with the geologic time scale. It is imprecise, so usually we have a time range versus a specific date. Geologic time scale, you've got different chunks, right? So we've got super eons, which is the largest division of time. But we're not going to focus on that one as much. I want you guys to remember eon, era, period, and epoch. So eon is thousands to millions of years, era is hundreds to millions, and period is tens of millions of years. Epoch is about several million years, and it's marked by differences in life forms that vary from continent to continent. So it's more regional differences than global differences. Age is the smallest division of geologic time, so it's just covering a few million years. And this is typically marked by changes in processes and events in Earth's history. So things that we can find physical evidence. So mountain formation, volcanoes, tectonic plates shifting, those things, those bigger types of changes. So geologic timescale, 90% of the geologic history falls in the Precambrian era. So that is our biggest chapter of life to date. Scientists are kind of going back and forth about lately. They believe, well, they want to start a new epoch, which they want to call it the Anthropocene epoch. But there's not quite an agreement among scientists about when to classify the start date. So for right now, we're still technically in the Holocene, but some believe that we are in the Anthropocene epoch, in which human existence has been the major life form that's caused changes on Earth. So again, here's your geologic time divisions: eon, era, period, and epoch. These are the time divisions that encompass the entire life of Earth that we know of. So a mnemonic device that I use, and something that you can use to remember those divisions from the largest to the smallest, is eon met era for a period. It was epoch, almost like eon met era for a party. It was epic. So whatever helps you work, whatever makes those divisions stick, because you will need to know those. Here is a nice picture of the geologic timescale. You can see mass extinction. So typically, these um, these divisions are marked typically by some kind of mass extinction or some sort of large geological event. So we're going to quickly go over Earth's 5 major extinction events. First, we're going to talk about the Ordovician Silurian extinction. So this happened at roughly 445 million years ago. It is the third largest extinction event. So we lost about 60 to 70% of the species that were around. Most of those species were in the sea. They were just ocean animals. And because of global cooling and reduced sea levels, that is what led to that mass extinction. The late Devonian extinction was roughly 375 million years ago. So at this time, 75% of all species died, and those species were those that were in the shallow seas. So there was multiple reasons for this large extinction event: asteroid impacts, global anoxia, so lack of oxygen. So anything when anybody talks about an anoxic event, they're talking about lack of oxygen. Plate tectonic event changes, sea level changes, and then there was also some climate change that occurred. The Permian extinction occurred roughly around 252 million years ago. 96% of all marine species and 70% of the terrestrial vertebrates. And a vertebrate is an animal that has a spine. Of those species died. The largest known extinction of insects as well, and it was caused either by meteor impacts, massive eruptions, climate change, and then climate change brought on by underwater methane. The Triassic Jurassic extinction. This happened roughly 201 million years ago. 70 to 75% of the species died. It occurred in multiple phases. So it didn't happen all at once. It was just kind of like a snowball effect. So caused by climate change, eruptions again, volcanic eruptions, and then some asteroid impacts. The most popular is the Cretaceous Tertiary extinction. This happened roughly 65 million years ago. This is what around the time that the dinosaurs died out. So about 75% of the species died. This was caused by climate change and also asteroid impacts. Again, you can take a look and you can see the different mass extinctions along here on the left hand side. And just in case it wasn't clear, we start kind of just like when we're talking about relative dating. The oldest, the oldest is at the bottom, and the youngest is at the top. Okay, so this is 4,000, sorry, yeah, 4,000 million years ago, 250 million years ago, 550 million years ago. Human existence on Earth. So even though Earth is about 4.6 billion years old, humans have only existed for about 1.8 million years old. So if we're talking about a timeline of Earth, this is the beginning, and this is today, and we literally just showed up yesterday. Our next topic we're going to move on to is fossils. Okay, this is a fun one. This is definitely one of my favorites. And I'll definitely make sure that we put out some fossils for everyone to take a peek at. So a fossil is just a preserved remain. It's a trace or trace of an ancient organism. Just something that was around before, might not be around anymore. They are not the remains of the actual organism itself. Typically, they usually are rocks, mostly found in sedimentary rocks. What can be a fossil? Typically, there are insects, dinosaurs, plants, animals, hard bodied organisms. Soft bodied organisms, because they don't have much to kind of hold on to, they don't tend to fossilize very well. So, what will fossilize best is a hard bodied organism. Anything that has bones, teeth, some kind of cartilage, anything like that. Soft bodied organisms don't tend to fossilize as well. So, when we talked about absolute or I'm sorry, when we're talking about relative dating, we use index fossils to help us kind of identify the age of a rock strata or layer. And this is just kind of this, this slide is just a quick refresh on that. So an index fossil is a fossil that is usually a fossil that about an organism excuse me, that is widespread, abundant. You can find it almost everywhere, but it was short-lived. So there's a very small amount of time that it existed. And so that's why we can use them to kind of figure out the age or relative age of certain layers. So trilobites, my favorite, is an index fossil for the Cambrian period. Ammonites are index fossils for the Cretaceous period. Again, this is a slide that I showed you in my last lecture. This is about how we can use index fossils to relatively age rock strata. So how are fossils made? We've got death. Death is how it starts. So an organism is going to die. It's going to be buried very quickly, typically. The best fossils are going to be very quickly because we don't want scavengers going through and taking bites and spreading the bones. We want the most well-preserved ones are buried quickly. Sediment surrounds the hard parts. It compacts and cements, or it cements and compacts, and the hard parts essentially dissolve, and a mold can be formed. Minerals are going to crystallize inside that mold, and a cast is formed. After millions of years, the fossil is going to be exposed on the Earth's surface, whether out, after a erosion, after just millions of years of erosion, or typically, sometimes when we have mining occurring in an area, sometimes you can find fossils that way too. Next up, we're going to talk about the types of fossils. The first type that I have a sample of is petrified wood. This type of fossil, though, is called a replacement fossil. So it's a mineral, it's when minerals replace the organic matter, so the living part. So in this example, uh, minerals have replaced the wood and the bark of a tree, and that's called petrified wood. A mold of a fossil, or the type of fossil which can be called a mold, is just kind of like a hole in a rock that has taken the shape of an organism and then that organism has died. So you can see on the right hand side two examples of molds. A cast is one that you can see a lot of sometimes. It's just a copy of an organism when sediments fill a mold. So at the top you have an ammonite, and then at the bottom you have a trilobite cast. Trace fossils are just a record of an organism's activity. So footprints, trails, burrows. There can even be, I have a fossil of raindrops, fossilized raindrops. So just that's a, trace fossil of the weather in an area. Another type of fossil, which is what scientists get most excited about sometimes, are original remains. So typically we don't find original remains. This is very rare, or it's not as common. So these typically are organisms that were trapped in amber, like you can see the mosquito that's been trapped in amber over here on the right hand side. Tar pits or frozen ground. This elephant down here, it's not even an elephant. It is a mammoth. This mammoth over here, mammoth. I can't. I think that's it. This little guy was buried in ice, and so he was very well preserved. They were able to take tissue samples. They were able to see what his last meal was before he was trapped and died in the tundra and surrounded in the ice, preserved in the ice. At the bottom right, you have a very, very well preserved mummy. And this guy fell in a tar pit or a bog, excuse me. So bogs, if you look up and you Google like bog people, these sometimes are very well preserved mummies, essentially, of people, and you can see how well it preserves. It preserves hair. It preserves the facial lines and characteristics. So these are really interesting ones because we can almost learn about cultures, ancient cultures, when we find these bogmen. Anytime that they're found, you can gain so much knowledge. This guy, you can see he's got like a rope around his neck. It was so well preserved. So we don't know if it was his if he was sacrificed, if he was, being punished for crime, but it gives us intel into cultures, ancient cultures. Something that I wanted to bring up to your attention is something called the Dino Walk. I've always tried to go, I've never been able to go though. So, Dino Walk is a collaboration between the Lucky Stone Quarry and Culpeper Museum. So, as I said, sometimes you can come upon different fossils in Virginia, and or not even just in Virginia, you can come upon different fossils. And in this case, they were quarrying for stone, and so when they were doing quarries, sometimes they just blast through layers. And at some point, someone found dinosaur footprints that date 215 million years ago during the Triassic period. So this is just evidence of dinosaur activity in Virginia. It's basically just dinosaur tracks that you can get to see. They only open it up once or twice a year, and you have to do a raffle to get there. It's completely free, but it's just an interesting opportunity for you guys to take. I think the next one is going to be this May. Okay, last last slide, is going to be a fossil fuel formation. You know that we use oil, we use coal, and this is just how it is created. You've got a warm and wet environment in which an animal dies, sinks, sediments are going to pile up, heat and pressure turn the remains into fossil fuel, like lignite, bituminous coal, and sedimentary rocks. Anthracite coal, remember, is the metamorphic version, but the rest are sedimentary rocks. And that's it. So just remember that and enjoy your activity.